Welcome to this presentation on the use of panelization of wall systems with cold-formed steel framing. These are the main points you should expect to know at the completion of the program. First, what types of buildings are appropriate for panelization, and within those buildings, which applications are appropriate? What are the benefits of panelization over stick frame construction? What does the process from the plant to the job site look like? We'll then get into some examples of buildings that used panels and move from there to options for floor systems with wall panels. We'll close out with some information on how you can be sure that you're getting a high-quality CFS product in terms of materials and their compliance with applicable codes and standards. We'll return to the subject of building types for panels a little later in the presentation, but I want to touch briefly at this point on the types of projects that are appropriate for panelized construction. As you can see from the pictures on this slide, panels are used for a wide variety of building shapes and sizes. These examples range from relatively traditional-looking buildings to some rather unusual designs. And the panel applications include a variety as well. The bottom right building, for example, includes decorative facade features and parapets that were constructed with wall panels to eliminate the need for scaffolding. The exterior finishes were applied in the factory. We have some more details on this project later, and we'll touch on building types more throughout the presentation. But the key point in this slide is that there are not many buildings where panelization is not an option. Even though this is a seminar on CFS wall panels, there are other prefabricated components made from CFS members that represent an opportunity for efficiency improvements. Often, roof trusses such as those shown above are provided by the same manufacturer or supplier as the wall panels. We'll also talk a little later about CFS floor trusses. And as this photo from an SFIA case study shows, cost savings are not just limited to cycle time or labor savings. Non-combustible construction has additional benefits, not initially obvious. CFS trusses eliminated the need for sprinklers to protect wood trusses and saved $40,000 on this project. The contractor estimated the prefabricated components in the building cut their construction time by 5 to 6 weeks. When panels are discussed, most people tend to think of the basic panel that consists of just the frame, as shown in the middle here. And although this is a common panel type, it's only the starting point with CFS buildings. For example, panels can be used for exterior walls, for structural or non-structural use, or single story in height or bypass framing covering multiple stories of a facade. There are also varying levels of components applied to the frame, including sheathings, exterior finishes, insulation, or wiring. Let's start with load-bearing applications. By applications, we mean what type of loads are being carried, where it is being used in the building, and what level of service it provides. For example, exterior wall versus interior, structural versus non-structural loads, or the level of finish applied to wall panels, or whether services such as wiring or insulation are included. As you can see from the slide, panels are used in a variety of locations for load-bearing applications, in walls, floors, and roofs. Even within a specific application, there are a wide variety of options. On this project, the load-bearing panels included exterior sheathing, versus this product, where load-bearing panels consisted only of the frame. The level of sophistication varies depending on the objectives of the project. At the very basic end of the spectrum, you might find panels such as these that are just the structural framing. As you can see by their location on the slab, panels on this site were used for both exterior and interior load-bearing walls. These panels are designed to carry a floor system above and then additional stories of load-bearing CFS. In fact, load-bearing CFS panels are often used in 4 to 7-story buildings, but can also be used in smaller or larger buildings. With load-bearing panels, 10 stories starts to be about the practical height limit without implementing measures to beef up members substantially, or otherwise introduce heavier beams and columns. This image shows a bypass panel that consists of the framing for multiple stories plus the roof parapet. This particular panel includes the exterior finish. It is open on the interior, which allows the crew members at the roof level and on the first floor slab access to attach the panel. Pre-finished exteriors offer a number of benefits, including unlimited stories. There are no height limits on pre-finished panel uses for non-load-bearing applications. In fact, they make a lot of sense on tall buildings since the finish is applied in the factory instead of on the side of a building. As we mentioned in the prior slide, they can be used with bypass framing on multiple stories. This 36-story building was a perfect fit for CFS panels. The design team not only selected panels, but decided pre-finishing the exteriors was the way to go. I'll take you through some slides of a project where the exterior facade was built with panels. This is a panel ready for installation of exterior tiles installed in the plant. This is the same project with sheathing in place on some of the panels. A dry location is critical for setting tile, and that's what you're going to find in the plant. No weather delays here. The panels are ready for transporting to the site. The interior is open to allow access for connections, insulation, and utilities as needed. Here we see the panels being installed at the site. This is another example of pre-finished panels from a project shown in an earlier slide. They are fully sheathed and finished on the exterior with EIFS. The entire front wall was installed in a few hours. The panels are secured top and bottom during the initial installation. Like the other example with tiles, the inside is accessible to allow for panels to be welded and for wiring and other services. We've talked about different types of panels and their uses in a building and pre-finishing, but there are a lot of other things you can do with panelization to reduce the on-site installation time and labor requirements. Pre-insulating of built-up members often is done in the plant because these spaces are sometimes inaccessible once constructed. With stick framing, the framing crew would need to insulate some spaces as they frame the walls, which is difficult to coordinate in the field. You can see some stud packs that have been pre-insulated here. Another way cladding saves time and on-site labor is that the water-resistant barrier is installed in the plant. This reduces cycle time connected with stopping construction to allow for the barrier to be installed and inspected on site, since these steps can happen offline in the plant. As mentioned earlier, even though our emphasis is on walls, we will cover some options for floors and roofs as we go through the presentation today. SFIA is also asked on occasion about panels for partition framing. There are no real technical reasons why interior partitions can't be used, and some panelizers do use CFS partition panels. In some buildings, where interiors are finished later as spaces are leased, it may not be a practical alternative to panelize a small number of walls. Although it would be great to install a complete wall, there are still some parts of a wall that don't do well when moved around and shipped. Movements are not good for drywall. The repair time after installation takes away from the benefits of pre-installing drywall. Likewise with windows, they are very expensive items and you wouldn't have to break many to lose any benefits with installing them in a plant. With interior cladding such as drywall, access to the interior for inspections, modifications, insulation, wiring, and plumbing is often required anyway, so it's usually not a consideration for interior drywall in the plant. Before we move on to some of the benefits of CFS panelization, I want to again emphasize a key point on the applications of CFS panels. Basically, there are few applications where panelization won't work, although some require more planning than others. CFS and panels are also compatible with many different systems and even other building materials. For example, this panelized project includes red iron as part of the framing and reinforced masonry walls. Note that the panel being lowered is a CFS floor panel. Speed is a significant benefit of panelization because of its impact on cycle time. Getting into a building faster can lead to revenue earlier than with slower construction methods. And in a business environment with labor shortages, it is important to note the labor impacts. With panels, the need for skilled on-site labor is reduced by pushing fabrication back to a plant. It also reduces the amount of scaffolding and other measures that require costs to rent and labor to set up, maintain, and tear down. Furthermore, plant construction is accurate construction. Weather and other factors such as untrained labor don't have the impact you get with stick construction. Plant construction is planned in detail. The result is better quality and reduction in hidden costs, such as callbacks or field modifications or repairs. As to speed of construction, panels just go up faster than stick framing. They can be done in so many different varieties to fit the needs of each project. Look at the walls in front of you and think about the effort it takes to stick frame something that tall versus building it on a table and lifting it into place with a crane. In real-life projects, contractors have estimated 5 to 6 week reductions in construction schedules attributable to the use of panelization in CFS buildings. On one building, the owner estimated $100,000 in unexpected rent revenue due to the quicker construction schedule. Details, even complex ones such as those shown with the arrow, are done on a table, not in the air. This reduces time on site and safety issues. No large crew on site is needed. These panels had one person at the bottom, one at the top, and the crane operator to initially attach these panels. A welder then attached the panels to each other on the inside, standing on the floor as opposed to standing on scaffolding. To further illustrate the benefits of CFS panels, I want to show you an example of a project in Green Bay where panels were used in a variety of applications. Note this is a 7-story building designed with floor and wall panels, and it was dried in 20 weeks at a cost savings of $250,000 compared to stick framing. The building consists of CFS wall and floor panels built around concrete stairways and elevator shafts. This is the building at the beginning of February. Here we are 12 weeks later with the 5 remaining stories of panels installed by an 8-person crew. It's a remarkable pace for a building of this size and height. What are some of the other pros and cons of CFS panelization? The planning and detailing required for panels is both a pro and a con. The detailing with panels leads to improved quality and a smoother installation process. On the other hand, it does add to the upfront complexity compared to stick framing, especially if the panel has finishes or utilities installed in the plant. But overall, the end product is a net benefit. There can also be a lot of on-site waste with stick building. Conversely, in a plant, the ability to plan cuts for members to length maximizes efficiency and almost eliminates waste altogether. Fortunately, steel is recyclable, so waste generated on-site or in a plant is typically recycled into new products. Plant recycling is almost guaranteed, whereas that's not always the case with stick-built structures. I mentioned before that panels can help reduce the amount of time and cost dedicated to observations and inspections. Last on this slide is that panels can add to the cost of shipping, although it's not significant enough to erode the overall benefits of panelization. The next series of slides will give us an overview of the panelization process from the factory to site installation. Most panels are fabricated in a plant remote from the job site and shipped by truck. In some rare cases for very large projects, contractors have set up a plant on the construction site. On-site fabrication requires a significant amount of staging and fabrication space, and it can reintroduce weather as a factor. This is an example of a wall panel fabrication table, or jig. The top and bottom tracks are installed flush against the metal guards you see sticking up. Note, in addition to the studs and track, they have installed bridging and strapping and a couple of heavier members for high loads. The crew is doing a quality control check with a diagonal measurement to check for squareness. The tables are waist high to reduce repetitive motion injuries associated with bending and lifting from the ground. This is a screw-attached panel that requires flipping to access the other side. Many panels are welded and don't require flipping. This shows a machine that flips the panel to allow for screws on both sides. Notice that there are offline components to the process. You can see built-up members that were fabricated elsewhere in the plant and brought to the jig table on the blue cart. Built-up members can be pre-insulated before going into the assembly, since they are sometimes not accessible once installed at the job site. After fabrication is complete in the plant, the next step is shipping to the site. It's not uncommon to get from 500 to 1,000 linear feet on a truck such as stacked on this one. It's important to stack panels in an order that allows the first ones needed to be accessible on site. Or if you bundle panels, stack the bundles with their end use in mind. Also, coordinating the shipment to the site is important. You need to consider things such as whether there's a staging area, placement of bundles or panels in the staging area, and access to them when needed on site. We'll address some of these issues in more detail later in the presentation. When arriving, you need equipment to be available to take panels off the truck. This is a staging area at one project site. This is something that also needs to be planned for up front so there are no surprises when panels arrive, especially on tight sites where open space is limited. The staging area helps to organize and keep the installation flow going. Don't block yourself in by how you store panels. Make sure that they're accessible for the crane or other moving equipment. Of course, staging of materials is not just an issue for panelized construction, but the size of panels makes it more of a critical planning task than with stick-building materials. A lot of this is more common practice for trusses that you already use on most projects, and the concept is similar with wall panels. As you see here, space can be at a premium for a staging area on some sites. In addition to the panels themselves, you want to be certain that there is adequate space to bring in and operate the equipment needed to unload, store, and move the panels. Having adequate reach for a crane to install the panels through the end of the construction is critical. Keep in mind, when planning reach for a crane, that some CFS buildings are being constructed to 6, 7, or more stories above ground level. This is another staging area on a project. Notice the method they use to store and move some prefabricated components. Not all panels need to be moved with heavy equipment. In fact, one benefit of CFS panels over other panel systems is that they are much lighter in weight. They can easily be tilted up by a small crew. But for very large panels or multi-story buildings, you're going to have to bring out heavier equipment, such as the crane being used to pick up this stack of panels. A spreader bar is used on the top to keep the load from damaging the panels, although it's not clearly visible in this slide. You can see the spreader bar in this slide. This shows panels being lifted into place. Although they are standing on a flat and stable floor, installers are tied off during initial setting for safety. The panel then becomes part of the fall protection system. Note the guide wires at the top near the header used to help this particular panel. The two studs used for diagonal bracing are being held with just 1 or 2 screws where they overlap. This allows the screws to be easily removed to adjust the panel as needed and then re-screwed. Floors are pre-marked for panel location. The track is still in place at the door bottom for stability during movement. Some panel companies remove the flanges and just leave the web. It's later cut off after the panel is installed. Notice the marking on ends of panels. Some plants also mark with red directional arrows, but there are lots of different methods used. The important point is that they are marked so the installers know where the panel goes and what direction the panel is to be placed. Some plants are more sophisticated and use barcodes and panel numbers to ID members. But note that they still use red markings for on-site installers. The eye bolt on the bottom panel is used to lift panels. It avoids the need for extensive cables or wrapping when lifting and moving panels. This is the bottom side of the same panel. They simply unscrew the bottom bolt and the eye bolt falls out. This is a nice time saver compared to other panel moving methods. The bolts can be taken back and reused in the plant. These next few slides show panels being moved from the truck once they arrive on site. In this case, they're moving bundles versus individual panels. Here's another shot of the same bundle being moved on site. This is one area that may require some change on the part of the general contractor. The method of picking panels and bundles should be designed in advance to handle the loads and not damage panels. This is a means and methods issue and is not part of the CFS structural engineer's responsibility. If necessary, the GC or framing contractor would have to contract for construction engineering separately from the framing design. These are panels getting dropped on site for installation. Like all construction, it's critical to have a level surface for panels. This should be stressed in construction documents, and site checks should be made before any panels are set. Also, as shown in the pictures here, bracing is an important part of panel construction, both for proper installation and to secure the structure until the permanent lateral bracing system is in place. Components of the lateral bracing system, including strapping and structural sheathing products, can be installed in the plant, further reducing on-site labor time and increasing installation speed. We won't go further into bracing, but there is an abundance of design guidance for the structural engineer on developing an appropriate bracing design. One example from the Cold Formed Steel Engineers Institute, or CFSEI, is shown here. Although we introduced this topic earlier, I want to get back to the different types of projects that match up well with panelization. As you can see from the different pictures, it's hard to tell just by looking at a building whether it has been or should be panelized. So what are good candidates? The short answer is that most any building can be panelized, with few exceptions. It's not just the building type or use that determines the applicability. Sometimes issues such as unusual designs or even slope or the presence of nearby structures or natural features that reduce access are the determining factors. That being said, there are some building types that are a better fit than others for panelization for the load-bearing part of the structure. One can make panels work for just about any building. However, there are some efficiencies when the same panel can be used multiple times in the same building. With many multi-story buildings that use CFS, the walls are typically aligned from floor to transfer loads, often with the upper floors a duplicate of the first floor. A similar or identical panel layout can thus be used for all stories and even for similar rooms that are repeated throughout the same story. In many hotels, such as shown here, the upper floors for the sleeping rooms are often identical layouts to the first floor. Panels can also be used on the one-story sections. This is a section through a building showing repetitive stories with loads carried to the foundation. Again, this is not a prerequisite for panelization, but it can be helpful for load-bearing CFS framing. Here is another view of a section through a building showing the same concept. Note that the loads are carried vertically down either to the foundation or to a transfer beam. Sometimes the loads might be carried to a structural steel or concrete frame that is typical with podium construction. But the key point is that the panels can be less complex if relying on light frame construction techniques, where the walls carry loads to the foundation, as opposed to offset alignments where special beams or columns need to be provided separately or built into the panels. This is an example of a transfer beam at the first level. This allows more flexibility in tenant spaces on the first floor. For example, you might see this in buildings with retail on the first floor and offices or residential spaces above. This is an example of a building being panelized over a first floor podium. This is early in the project with the podium and the first story panels in place. I'll go through a series of slides and note some of the milestones on this project. Note the date of March 30th and the 3 stories in place over the podium. And here we see additional stories on the main building and construction starting on the attached structures in the lower left. And now we have 5 stories up on the main building. And 6 stories on the main building. Smaller buildings are closed in with panels at the same time. And here's what the building looked like 2 months after the first floor photo shown earlier. And slightly later. And 6 weeks later. Apartments with parking underneath are also good candidate buildings for load-bearing panelization. Notice the duplication of framing layout as you go up the side of the building. Another example of a panelized building under construction. In fact, multi-story residential buildings of all types, including the barracks shown here, are generally good fits for load-bearing wall panelization. Notice the access on this site leaves plenty of room for the equipment to move and set panels. The next few slides are also good examples of building types that are good candidates for load-bearing frame panelization, but they also stress the importance of coordinating materials and equipment on the job site. And here we see dorm buildings. In fact, CFS is often used in the student housing market due to its flexibility, durability, non-combustibility, and competitiveness with other building materials. Notice the cranes in the background and the building layouts that leave room to maneuver. The cranes need to be located where they can reach the farthest and highest points of the finished building. The building spacing also allows space for panel storage, staging, and movement around the site. This is an assisted living facility, which would usually be a good candidate for panels. However, note that crane reach and storage or staging room can be an issue with a layout of this type, where space on the ground and for access is limited. The buildings under construction are pretty tight against each other, and the completed building in the lower left corner. Once the courtyard structure was started, there was even less space. All of this emphasizes the need to sequence construction specific to each project. One great thing about wall panels is that they are as compatible as stick-built framing with other components, including floors. The systems you used for prior CFS buildings should be just as applicable with panelization. Some manufacturers even take it a step farther and panelize CFS floor framing. That's a topic for another seminar. Let's start with the most obvious from a CFS perspective. Conventional CFS C-section floor joist with various top and bottom sheathings. The floor system really isn't much different with stick or panel wall framing. Although these systems can be used and are done so frequently, the fire-resistant ratings required for the type of construction will dictate the design. Specific UL or other designs for fire resistance must be installed consistent with the assembly as tested. Sort of in the same category as C-sections are CFS floor trusses. I'll just quickly scroll through other examples of the other types of floor systems that have been used with panels, so you get a good idea of the broad range of systems available. This shows a concrete steel deck floor system. This is the top view of deck pans from a project with composite steel deck and concrete. Here's a cast-in-place floor system with CFS wall panels and concrete plank floor panels. Here's the same concrete plank system from the bottom. Bar joists were used on this project. Again, we've shown the major types of floor systems you might encounter. You can see that panelized CFS walls are compatible with all the major floor systems used in today's construction. Independent of whether you are panelizing or stick building, code compliance is important. With cold-formed steel, the SFIA code compliance certification programs give contractors and suppliers the assurance that the cold-formed steel products they purchase from SFIA members meet the highest standards of quality and the latest provisions of the building codes. The programs are administered by a recognized independent third party that periodically performs unannounced visits to plants and audits individual products. Stud and track products are tested for their mechanical properties, coatings, dimensions, and other requirements in applicable codes and standards. The SFIA programs ensure code-compliant material for all applicable product produced by SFIA member companies. The programs include quality control and quality assurance components and are the only CFS programs to include unannounced plant audits to document procedure and retrieve and test materials by a third-party administrator. There is a program for structural members, non-structural members, and for connectors. To find companies who are certified under the program, visit the SFIA website at www.cfsteel.org. In addition to the code compliance programs, the SFIA Contractor Certification Program enables professional contractors and truss fabricators to distinguish themselves in the competitive landscape by demonstrating proficiency in cold-formed steel framing. Certified SFIA contractors receive recognition for continuous improvement, education and training, and quality control systems, all of which are independently verified via a written test and rigorous observation of CFS installation techniques. Certified contractors adhere to the SFIA quality management system and code of ethics, which promote industry standards that ultimately lower costs and speed approvals. Before we conclude, note that what we covered today is not an exhaustive list of everything you need to know about panelization. However, by relying on SFIA manufacturers and contractors, as well as qualified CFS engineers, panelization is something that you can use on your projects today. The infrastructure to panelize and take advantage of its benefits is well established for cold-formed steel construction. Thanks for your participation today. For more information, visit the SFIA website at www.cfsteel.org.